Hello everyone, Daniel Dallas is right here. And we continue doing differentiation. This is not just the basic concept. Otherwise, it's going to be application. So, application particular in economics because actually you can apply derivative tools and general differentiation techniques in every single area like in finance, in economics, and engineering, science, and physics, and so on, right? There are basically a sheer volume of areas that you can apply this tool. However, here we stick to application in economics. It's going to be useful for A-level maths as well as for IB students because those students who explore application within IB syllabus actually might find this very useful. Alright, so if you remembered in previous video, we done differentiation and I actually explained you how to differentiate um, those stuff, what you can see right now. And we had a little touch of application in economics because we were calculating marginal revenue function and total cost. That was a little rehearsal, so make sure you know how to differentiate, you know the basics, you know the all rules of differentiation, and especially functions with two or more terms. That's the key concepts, and their more testable functions types. Okay, and we're gonna go to the next episode where we apply that tool in economics. Here are 4 problems, and let's get to the point. So as always, grab your pens, grab your notes, try to do by your own, and let's see how this might work. So the first problem, a product has supply function Q versus price, basically quantity versus price, and demand function, okay? The same quantity demanded as the function of the price. As you can see here is the negative slope in general, and here is the positive slope if we consider them as straight lines, all right? And here is a brief illustration how this looks like. Okay, so you have -10 with a positive slope somewhere like this. That's going to be supply function, and demand is going to be going down or dropping down straight line starting with from 80. So that's going to be y-intercepts, and that's going to be a sloping down curve, or in this particular case a straight line. So that's normally how you know them from economics and from this science. But for this particular case, you just simply need to find inverse function. So what does mean inverse? Like for a general function, if fx is like direct function, so inverse, which is denoted as f to the power -1 from x, basically becomes the function of x of y. So it means that first of all you need to express the argument x as the function of y and then swap x and y. Okay, so that means inverse function f -1 from x becomes the function that simply represents this dependency as if x is y, or f to the -1, and y becomes their standard argument x. Okay, so I'll show you here. So right now we have q as the primary function and p as the argument, okay? So what do you need to do? You need to express p through q. So for inverse function in this case, it becomes the function p from, but not x, but from q as the quantity. Okay, so let's do it. Let's express from supply. So for supply, it simply becomes p equals 2. So you transfer -10 to the left side, you've got q plus 10, and finally you need to divide by 100. So that's already the inverse function because right now you have p from q, but if you want, you can partially divide by 100 each part in order to get the straight or the standard equation of a straight line. So it becomes 0.01 of q and plus 0.1 because 10 over 100 becomes simply 0.1, all right, or 1/10. So for demand, we do the same, and for demand function, we simply do straight things similar to what we've done here. Okay, so we're gonna transfer q minus 80, so we're gonna transfer 80 to the left side, and everything divided by -50, that becomes the function price of q of the quantity. But I'm not satisfied with that, and I would like to divide both terms, q and -80 by -50. So it means right now we have -1/50, but it's better to convert into decimal. So you can use calculators, but if you're good in mental math, you'll get a -0.02, right, of q, and so plus 8/5. But 8/5 you can even more convert into fractions. So 8/5 becomes 1.6, and that's become positive. All right, so we've done the first one, the first problem. Let's see what you need to do in the second problem. So here, a product has a supply function and demand function. Find the market equilibrium. Again, so equilibrium becomes or happens in this point where demand curve and supply curve are intersected, because in this simple case there are straight lines. That's basically the primary example for those functions, all right? But I'm not going to graph that again for this particular functions. I'll just simply equate both sides to each other, because you know that in equilibrium, or where two graphs intersect with each other, both x and y coordinates the same. So in our case, q and p are going to be the same in the equilibrium point. So you can simply write down the equation for equilibrium. So you equate the left side as well as the right side. So that's why I just equate the right sides of those equations to each other, and minus 2p, and from where I can calculate the equilibrium price, I transfer -2p here to the left side, and I'll get 5 pi over here, and 300 transferred to the right side, so that means I'll get 1,500. We're not stated which units for the price, so it's going to be just simply, you know, I don't know, just no name currency for that. And now what we're going to do, we need to divide by 5. So that's why equilibrium price in equilibrium becomes 1,500/5, which is simply 300. All right, so that's equilibrium price. And to find equilibrium units of quantity, you just need to plug this parameter 300 instead of price, for example, here or here. Doesn't matter, because you should get the same result, absolutely the same for both equations. So that's why equilibrium quantity becomes 3 times 300, and on top of that plus 300 there. So that's why equilibrium quantity becomes 900 plus 300 becomes 1,200. All right, now that's going to be equilibrium quantity. And let's move to the next question, question 3. So I would do it here, and let's consider right now question 3. So find the maximum value of the following expression. So fx, basically it's a parabola. I'll show you 2 ways how to use, because they are not stated which way to use. Obviously you need to use differentiation, but first of all I'll show you through the vertex, all right? So how to find the vertex? Basically, you remember, okay, I just do, that's a quick layout, and first we're going to use the vertex concept, vertex of the parabola, because right now you have quadratic function. So that means we can use this approach, and let's remember how the vertex is calculated. So for x vertex, we just simply need to write the formula minus b over 2a, or if you want, if you have like those skills to get the complete square form, So complete in square and rewrite this quadratic equation from the standard form into complete in square, you're welcome, but I don't recommend to do that. So that's why I'm just gonna use this formula, okay? So minus b over t, where x squared plus bx and plus c is our general equation of the function. As you can see here, by comparison, coefficient a is -4, coefficient b is -8. So right now we just need to plug those coefficients here, and we'll get minus 8 over 2a means -8 as well. So that means you have -1. So x vertex is -1, and to find y vertex, you just simply need to plug this -1 back again into our equation. So it becomes -4 because x squared is -1 squared becomes positive, and minus 8 times -1 becomes positive 8, and minus 3 on top of that. So we'll get 8 minus 7 becomes 1. So that's why the maximum value of the following expression is 1, and I just simply can show you the sketch. So right now we have the vertex. I just lay out more accurately. Sorry, not down but upward, and here's to the right. And I'll sketch the parabola. So it goes somewhere through -1 because it's x vertex, and this simply becomes the axis of symmetry. So here's just interpretation how the graph looks like, okay? And it's upside down because of the a. So when a is negative, it means branches down, and that's going to be the maximum value of the function, which is 1. So all is okay, and agreed to our results. Okay, so we don't care about right now where x-intercept occurs, so we're thinking about only this vertex point according to the question of this problem. Okay, and for the second case, for the problem 4, I will show you through differentiation. Okay, I'm not gonna just repeat the same stuff for problem 3, so that's why we just go straight to the problem 4. Okay, however, no, let's do it for problem 3 as well. Okay, so the way to, because it takes actually, we just need to be sure that x vertex is -1, so let's just differentiate. So you taking dy dx or f prime from x of this expression, and then this becomes -8x and -8, from where we equate it to 0, because you remember that derivative represents the gradient, and at the maximum point or at the minimum point, the gradient or the slope of the tangent line becomes basically 0, because your tangent line is horizontal. So that's why you equate f prime to 0, and from where you can get that x vertex is -1, and that's the same, absolutely the same that we've got through the formula. All right, so let's do problem 4 right now. So for this problem, you need to find a minimum value of the following expression. I just rewrite the following expression more clearly. So f from x is 2x squared plus 6x minus 4. And right now you need to do absolutely the same, so I'm going to use differentiation tool. So that's why f prime from here, from x, is, let's differentiate, so it becomes 4x and plus 6 on top of that, and you equate it to 0, from where x becomes -1.5, because it's -6 over 4. And right now what we're going to do, we need to plug this value, so that becomes the vertex or the x-coordinate of the minimum, okay, because in our case parabola goes upward and the vertex is the minimum point, so that's the minimum. And we need to find the y value, so just simply plug -1.5 into the equation, so we'll get 2 times, so 1.5 squared and minus 6 times 1.5 and minus 4. Okay, so what I got y vertex is negative 8.5, and that becomes the minimum value. Okay, one more time. So that's the minimum value of the function. All right, so we discussed those 4 problems, which are not really hard. This is basically, you know, just the easier level. It's a very medium one, but those basics you need to know, all right, in order to apply this tool in economics. And let's move to more challenging problems.